Find the normalized eigenfunctions of the boundary value problem. So we have an ODE and two boundary conditions. So first we find the eigenfunctions, then we normalize them. To solve this boundary value problem, we consider three cases. The case 1, lambda equals 0, then lambda negative, then lambda positive. So in this case, this ordinary differential equation becomes just y double prime equals 0. And if we integrate twice, then we get y equals ax plus b as a solution of y double prime equals 0. Then to determine these constants a and b, we apply these boundary conditions 1, 2. Okay, using the first boundary condition, that is y at 0 equals 0, so 0 equals 0 plus b, so b equals 0. Okay, and using the second boundary condition, since b is already 0, when we differentiate this, we get y prime equals a, and use that we get a equals 0. That means this solution is in fact just a 0, and we call that trivial solution. So y is always 0. That means lambda equals 0 that we consider in this case is not an eigenvalue. Okay, let's move to case 2, where we take lambda negative. To make things simple, let's say lambda equals negative mu square, where mu is positive, so that this is still negative. Okay, in that case, the ordinary differential equation y double prime plus lambda y equals 0 becomes y double prime minus mu square y. Lambda is being replaced by negative mu square, and this is a second order homogeneous linear differential equation. To solve, we find the characteristic equation r square minus mu square. The characteristic equation is r square minus mu square equals 0, and solve for r, we get r equals plus minus mu. Based on these roots, we have the solution, some constant cosine hyperbolic plus b sine hyperbolic mu x. Okay, now we use the boundary conditions to solve for a and b, to determine these constants a and b. So using the first boundary condition y at 0 equals 0, we get, so this is 0 when x is 0, so cos or cosine hyperbolic 0, which is 1, and sine hyperbolic 0 is 0. Okay, this will be 0 and this will be 1 when x is 0. So we get a times 1 plus b times 0, that means a is 0. So this solution, now we can update this solution, and this becomes, when a is 0, we just have now b sine hyperbolic mu x. So the solution is b sine hyperbolic mu x. Now to determine b, we use the second boundary condition. Second boundary condition was y prime at 1 plus y at 1 equals 0. It's got prime, so let's find the derivative of this. So sine hyperbolic mu x, mu outside, b constant, cosine hyperbolic mu x. Now using the second boundary condition equals 0, so I'm going to write 0 that in the right hand side. So y prime at 1, so plug in x equals 1 here, so we get mu b cos mu plus y at 1 here, y at 1 mu, that means b sine hyperbolic mu equals 0. Okay, now we solve this equation for b. Let's factor b out, and for now let's assume b is not 0. Okay, we are just assuming b is not 0. This might be wrong, we'll see in a moment. When we factor b out and b is not 0, then we get mu cos mu plus sin mu equals 0, and moves sine hyperbolic on the other side, sin or sine hyperbolic on the other side, that becomes negative, and divide by cos. So we have mu equals negative tangent hyperbolic mu. Now we need to solve this equation. Let's say this is like x equals negative tangent hyperbolic x. Okay, to solve this equation for mu, obviously we need to graph left hand side. Let's say y1 equals x and y2 equals negative tangent hyperbolic x. So when we graph, this is y equals x, identity line, and using calculator we can graph negative tangent hyperbolic. This is this case. In fact, tangent hyperbolic is just tangent hyperbolic of any angle is sine hyperbolic over cosine hyperbolic, and we know that sine hyperbolic is 1/2 e theta minus e negative theta, and cos is 1/2 e theta plus e negative theta. Half cancel. If we graph this, we can simplify further, but e raised to x minus e raised to negative x over e raised to x plus e raised to negative x. In fact, we can divide top and bottom by e raised to negative theta. Okay, and you get simpler. But if you graph, then this is the graph of negative tangent hyperbolic, negative in the front, and we can see they intersect at origin. But we said when we assume lambda equals negative mu squared, we assume that lambda is negative, that means mu is positive. But the only place where these two curves intersect at mu equals 0, that cannot happen because our mu is positive, so there is no solution. Okay, but since mu is positive, there is no solution. That means what we assumed earlier, b not being 0, is false, so we must have b 0. That means we get a trivial solution because we found a equals 0 earlier, now b equals 0. Okay, thus negative lambda is not an eigenvalue because we don't have non-trivial solution. Now case 3, we take lambda positive. To simplify our work, let's say lambda equals mu square, where mu is positive. Okay, then the ODE, that's y double prime plus lambda y equals 0. This becomes y double prime plus mu square y equals 0. So lambda is mu square. Now let's solve this. We find characteristic equation as earlier. So r square plus mu square 0. Move this over, becomes negative. Then we get plus minus mu I. Okay, because negative mu square. Now based on this, we get cosine and sine mu x as solution. So the general solution is a cosine mu plus b sine mu. Now we use those two boundary conditions to determine the values of a and b. First, the boundary condition y at 0 equals 0. So that means 0 equals a cosine 0 is 1, so a times 1 plus b times sine 0, which is 0. So basically we get a 0. Now we can update this solution because a is 0 means we don't have this anymore. So the solution is y equals b sine mu x. Okay, so this is the solution now, updated, but we need to determine b. And to apply the second boundary condition, look at here, y prime at 1 plus y at 1 equals 0. Let's find derivative of this. Derivative is just mu b cosine mu x. In fact, why we are finding this? Just to use second boundary condition. And use the second boundary condition. So here y prime at 1 is mu b cosine mu plus y at 1 is up here. This is y. So y at 1 is b sine mu equals 0. Let's solve for b. Factor b out like earlier, and for now assume b is not 0. If b is 0, then we get 0 equals 0, so we get trivial solution. So to get non-trivial solution, let's assume for now, we don't know if it is possible, but for now let's b not equal to 0. Then we get mu cosine mu plus sine mu equals 0. And let's move sine mu on the other side and divide by cosine mu, so we get mu equals negative tangent mu. Okay, now we need to solve this equation 1. I'm just naming equation 1 for future reference. So all we have to do is graph like x equals negative tangent x. So first graph y1, first curve as x, and second curve is y2 equals negative tangent x. So when we graph, we get this. Okay, so this identity line is y equals x, and we get bunch of graphs for tangent x, negative tangent x, by the way. Okay, and we are not worried about negative part, so we don't have to worry about this. Just looking at here, and 1 0, we don't need that part because mu is positive in our case. So the first 0 will be here, that's the lambda mu1, and when we square we get lambda 1, first eigenvalue. Second here, third here, and if you notice, these points of intersections are coming closer to these vertical asymptotes. This is pi over 2, this is 3 pi over 2, 5 pi over 2, 7 pi over 2, and for n bigger than equal to 4 or 5, they will be almost equal to odd integer pi over 2. Okay, so let me write in this way. So from the graph we find that first mu1, that's the first point of intersection, just from calculator we get 2.029. Mu2 will be 4.913, mu3 is 7.979, approximately equal. And for large n, mu n will be very close to odd integer pi over 2. Okay, odd integer means 2n minus 1, like 1, 3, 5, 7, 9, 11, like that. Okay, these are mu. That means our eigenvalues, that's lambda, because we assume lambda is mu squared. So we square them. That means mu1 is square of this, lambda 1 is this, lambda 2 is this, lambda 3, and for large n, mu n is very close to this. Okay, so b should not be 0, then we have these eigenvalues, and in general this. Okay, and corresponding eigenfunction means just the solution is we have b, but we can take b equals 1. So sine mu x, mu is root, our lambda was mu squared, and not only we got 1, we got infinitely many, so we are writing n. Okay, so mu n is root lambda n. So eigenfunctions or the solutions are sine, taking b1, root lambda n x for n bigger than equal to 1. Okay, these are eigenfunctions, and our question was to normalize these eigenfunctions. Okay, and by the way, if we go up and look at this equation 1, and this is what we graphed and found the eigenvalues. Okay, this is this is coming from here, and these lambdas are in fact root, these mu are in fact lambda, root lambda, and there are infinitely many we found. So if we write it, we can write it in this way: root lambda n cosine root lambda n plus sine root lambda n equals 0. So this equation is called determinantal equation, because from this we were able to determine the eigenvalues. Okay, so from equation 1 we have this, so I'm putting equation 2 for future reference. This is called determinantal equation, satisfied by non-zero eigenvalues. Now our goal is to normalize the eigenfunctions that we found here, solutions. Okay, yn sine root lambda n x. To normalize, what we have to do is we just multiply by a nice constant. Let's say kn, multiply by kn, and we denote that by pn, so that this is true. integral 0 to 1 r, that is 1 in our case. Our equation is just y prime plus lambda y, lambda ry, r is 1, phi n square x dx equals 1. So we want to satisfy this condition. Okay, and basically we want to determine these constants kn's times this solution. This is a solution. When we multiply by a constant, we still have a solution satisfying this. That means let me write 1 in the left hand side. 1 equals 0 to 1, this r is 1, and phi n square x equals 1. Just writing this in backward. Let me simplify here. Phi n, we assume kn times sine root lambda n x. Phi n square means kn square sine square this, and we can pull kn square outside. Now we need to integrate sine square, and we know that sine square we cannot integrate it the way it's written. This is same as 1 minus cosine double angle 2 theta over 2. So 1/2 minus 1/2 cosine 2 theta. Here is case 1/2 minus 1/2 cosine 2 angle. Angle is root lambda n x. Now we can integrate this kn square outside, and we have 1/2 antiderivative of 1/2 with respect to x is just 1/2 x minus 1/2 is there. Antiderivative of cosine is sine, and divide by this angle 2 as well, and 2 root lambda n, and we have to, so 4 root lambda n. Now we need to evaluate it, upper limit lower limit, so we get this. Okay, once we evaluate, so we are here now. In fact, this is from here, this equals 1. We can find the values of kn and we are all set. But we can simplify this, so I'm simplifying, which is not needed, but this we can always use the determinantal equation to simplify this. Now what I'm doing here on the top is sine 2 theta, and sine 2 theta is 2 sine theta cosine theta. So 2 sine theta cosine theta. In the next step, 2 and this cancel, this 2, and we can combine these two fractions. So kn square, we get this, combining these two. Then we can replace negative sine lambda n from the determinantal equation. Okay, what is the determinantal equation? That's equation 2. Look at here. This implies, if we move this over, negative sine square of lambda n equals root lambda n cosine root lambda n. So I'm writing this for negative sine root lambda n. Okay, so we get plus root lambda n cosine 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 square, and in fact we can factor this root lambda n from these two terms and cancel with this. So 1 plus cosine cosine square root lambda n, that equals 1, by the way, and cross multiply, we get kn equals 2 over this root 2 over this, and kn times, in fact this kn times sine root lambda n x. These are the normalized eigenfunctions that I wrote here. Thus phi n x are root 2 over this times sine root n x, normalized eigenfunctions. Final